All right, recording is rolling. It is Monday, September 19th. So, um, oh, you guys are getting school pictures today. Yeah, school pictures. I hope you guys got that note posted to Google Classroom back on Friday afternoon, but there you go. Uh, I did have top scientist list for projectile motion, but I think I left that home, so I'll have to bring that in tomorrow. All right, back on Thursday and Friday, I did not see you guys. You guys were, well, other classrooms because I was Parker and Tussin here. But I left with your covering teachers some materials. Meant to, but I guess that was a kind of chaotic too because you guys had substitutes and blah, blah, blah. Okay. So I just now gave you guys in front of me the materials that were supposed to make their way to you. So I'll debrief all that real fast, and then we'll be moving on. So one thing was the split book. You guys see the split book? You guys ever made a flip book? Okay. So yeah, maybe so. If not, or if you have, then here's another opportunity. So you guys can make something cool. You guys get to apply your physics knowledge of kinematic motion and your imagination. So there have been a lot of really good ones. I've got some just within reach here. So we got from Cole, got a guy with bow. Oh, look at that projectile. Okay. See, if you get like frame by frame exactly where each the position of the arrow, then your brain can believe it. You're like, oh yeah, that looks like a projectile. I can believe that. Yeah. Got a water droplet. This one's from Brody. Bloop. Yeah, cool right there, right? Okay. Bee. Bee, bee. Yay, happy bee. Fun times. All right. So there were a bunch of good ones, but you guys get the idea. Flip book, some kinematic motion going on. All right. The other thing I gave you guys was this template. Okay. And I will give you guys a crash course on what this is, but if you want to see a more extensive version, then I posted a class video back on Friday about this. So you cut out both circles, and then you punch a hole in the middle, and you flip them together with the paper clip, so it'll rotate like this, right? Rotate like this. Okay. Now, imagine for a moment, let's say it's back in the 1960s. You guys are engineers working on the Apollo project. We're trying to send astronauts to the moon, ultimately. Do you guys have a nice digital scientific calculator in your pocket like this? No, these didn't exist back in the 1960s. So how are they making all those calculations, sending people to the moon back in the 1960s if they didn't even have this? Okay. Well, I guess they sort of had a more basic version of this that was like the size of an entire room, right? But not one you could hold in your hand. Okay. Well, they had slide rules, right? So they just like have how they it looked like a little ruler. It looked like a ruler. You could just like slide it back and forth. Okay. But the numbers were spaced weirdly. They were actually spaced logarithmically. Now, if you take that turn into a circle, you actually get this. So this actually is a slide rule. It's just in circular form, which is actually a better design for some reason. Okay, you don't have to. Well, it's easier because it like wraps around. Okay. So here's kind of how this works. Okay. You can one thing you can see is that you can align all the numbers inside outside, right? The 1, the 1, the 2, and the 2, the 3, and the 3. Okay. Get this aligned. Okay. There you go. So total lines up. All right. Now the numbers are spaced weird. There's a huge gap between the 1 and the 2. They get closer to 2 and 3. Right. And then by the time you get to like 7 and 8, and 8 and 9, it's pretty close together. And then 9 wraps back around to the 1. Okay, so that's interesting. It goes like 9, 9.5, 9.9, and then it goes back to 1. Now, this is kind of like a floating decimal place. So the 1 might represent a 1. It might represent 10. It might represent 100. It might represent 1,000. Right? So you kind of have all the numbers. You just have to keep in your mind a reasonable place for the decimal place to go. Okay? So allow the decimal place to float. Okay. Now, remember the numbers are spaced logarithmically. Now, watch what happens when you turn this. Right? And here's my go-to example. Whoops, actually did it the wrong way. Let's do it this way. Here we go. That's what I meant to do. Okay. Okay. So what if you, for example, align this inside 1 with the outside 3? Okay. What if you read that as a fraction, like a ratio, like a 3-to-1 ratio? You see 3 over 1? You see 3 over 1, right? Okay. Now, if I leave these two circles locked in place relative to each other and I look around the circle, hey, look at this, 6 over 2. Isn't that also a 3-to-1 ratio? How about 9 over 3? Ooh, hey, do you guys think that all the numbers all the way around the circumference are all the exact same ratio? Interesting, they are. Well, let's check one more. 1.2 over 4. Oh, wait, does that fail? But remember I told you guys that the decimal place floats. 12 over 4 is a 3-to-1 ratio. So it's 15 over 5. Right? You guys see that? Okay. So let the decimal place float, right? And then come up with something reasonable. Okay. Now that you know all the ratios are the same, you can take advantage of this with fractions to multiply and divide extremely quickly. For example, what if you didn't know what 6 over 2 was? I'm doing something so basic that you can't know what the answer is, right? 6 over 2. Well, I wonder what 6 over 2 is, okay? Well, since 6 over 2 is equivalent to the ratio of 3 over 1, the over 1, the denominator 1 doesn't really change the numerator, so the 1 like points to the answer. So the answer is 3. Again, not just for 6 over 2, but really for all ratios all around the circle, okay? So what if I want to do something really, really crazy? Like, I wonder what is, I'm just going to make up something on the fly here. What is 75 divided by 29? 75 over 29. Okay, now, at a glance, I'll say that's probably a little less than 3, I guess, between 2 and 3. I don't know yet. I'm not going to hit enter yet. But let's see what my analog calculator says. So I'll put 75 on the outside. So that's right here. I need 29 on the inside. That's like right there. All right, now these are locked in place. Okay. And then the inside 1 should point to the answer. I'm looking at, it's about 2.6, about. Right. Oh, and you know what? Actually, it can get even more. I wasn't sure it's going to be that precise, but it's like a tick under 2.6. It's like 2.59 something. Right? Look at 2.586. Yeah, so it nailed it. Got it exactly. Right. You know what else you can do with this? Okay, so you can multiply and divide, right? You can divide and multiply. Oh, I forgot to tell you guys how to multiply. Okay. Let me go back to my more basic example, just so it's more obvious. Right? If 3 over 1, for example, is equal to 6 over 2, you guys remember cross multiplication from cross multiplication? Okay. So this works on that principle. If you take this outside 3 times this inside 2, it will be this outside 6. So this 3 times this 2 is equal to this 6. Right? You pick any pair of numbers to do that with it. Okay. You can also take square roots. Now, you guys remember how square roots are like 1/2 powers? Like, what's the square root of 9? 3. 3, right? Okay. So if I pull this apart just to emphasize the fact that you don't need both circles for this, you only need one. If I find my 1 and I find my 9, what's halfway between 1 and 9, say going around the outside perimeter? So halfway around. Remember, it's halfway around logarithmically. Okay. So that's like 9 to the 1/2 power. That's exactly the 3. Look at that. It's exactly 3. Maybe we should start with the more basic one. What's the square root of 4? 2. So here's my 1. Here's my 4. 1 is like the home base. Here's 4. Okay. What's halfway around? Oh, it's 2. Look at that. Okay. Hey, what's the cube root of 8? Do you guys know the cube root of 8?
64. Yeah, 64.
Well, 8 squared is 64. I'm thinking, what times what times what is equal to 8?
4 times 4. I mean,
yeah, 2, right? 2 times 2 times 2. So you do 2 times here. Please spell that. 2 times 2 times 2 is 8. Therefore, the cube root of 8 is 2, right? Now, cube root as a power is a 1/3 power. So from here to here, from my home base of 1 to this 8, if I cut the journey into 3 parts and I say, what's the first section, like the 1/3 power on 8? Oh, it's 2. Look at that. Okay. So yeah, so now you guys know how to multiply, divide, and take roots with a couple pieces of paper. All right, that was fun. Oh, you know what else is fun? I left you guys off about a week ago with this mystery cup challenge. Did anybody figure this out? Or couple of holes in it. You fill it up halfway with water, it holds the water. You fill it to the brim and the entire cup drains. Did anybody figure out how this thing is designed? Okay. All right, so I'll give you guys a little bit more time to think about that. Come back another day. Okay. All right, now let's finally get to today's stuff. I got 3 guys lined up. Newton's laws of motion, and then a bunch of free body diagrams. We're going to be doing a bunch of free body diagrams today, but let's review these laws of motion. Now, hopefully you guys learned these like back in a middle school science class. Hopefully this is just review, but it's the physics context. Okay, so these 3 laws of motion that will govern everything well until we get to relativity. Okay, so the first law of motion, this is an object at rest will remain at rest, right? Unless there's an outside force acting on it. So if I just have this object sitting here, it's not just going to spontaneously jump off the table, right? But you know what else also doesn't change its motion is everything, right? So an object will maintain its velocity. And now you guys know from just the first few weeks of physics that velocity has 2 parts to it. Speed, which is magnitude, and also direction, because velocity is the vector value, right? So anything that is already in motion will maintain its speed and direction of motion, again, unless there's an outside force acting on it, right? So a classic question that you guys are going to see come up, we'll do a Kahoot one day, is the Voyager 1 spacecraft. You guys know back in the 1970s, there were these space probes that were launched into deep space, and they're like at the edge of our solar system now. They just like keep going, 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 right? How have they been going for decades? Like, could there ever be a situation where the fuel just runs out and you say, come to a stop? Will that ever happen?
No.
You are correct. That will never happen, right? Because once they're in motion, there's no reason for them to ever change their motion until there's an outside force acting on them, right? So they're just going, right? They're just coasting. They don't need any fuel, right? Once they're in motion. Now, your car might be different because there are a bunch of frictional forces acting on your car. But those would be outside forces. That's why your car slows down if you take your foot off the gas pedal, right? But the Voyager spacecraft, it's just going, right? This is also called the law of inertia. Okay, law of inertia is the first law of motion. Okay, you guys get that? Okay. So nothing will ever speed up, slow down, or change direction unless there's an outside force. Okay. Second law of motion. Now, my favorite version of second law of motion is this fraction right here. Okay. That says why accelerations exist. What causes accelerations? Now, you guys have been measuring accelerations for a few weeks in this class and applying accelerations. You guys know what accelerations are. You guys did whole labs on them, right? That's a rate change of motion. It's a rate change of velocity. Okay. Now we're going to say, well, what causes accelerations? Because we know from the first law of motion, nothing wants to accelerate unless there's an outside force. Okay? So what equation ties this together? Well, it goes like this. The net force divided by the mass of an object. Okay? Now, why did I say net force? Because there could be multiple forces on an object. Like here, I'm showing two forces. Okay? But there can only be like one net force, right? Maybe they could do like Pythagorean theorem, some version that add those together. Okay? Even though there might be many forces, there could only be one acceleration, right? So there's only one corresponding net force. Okay? You guys see how, according to this fraction, if you like triple the net force, triple the acceleration for the same mass, right? Triple this, triple this. So that's a direct relationship. The harder you push, the more it accelerates. That makes sense, right? Okay. But also see how the acceleration is inversely proportional to the mass, right? Like, I need a whole box of lab weights up here. Guess you guys have make believe. Okay. Make believe. I put a force on this guy, and it accelerates some amount. And then what if I tripled the mass? Like, oh, now it's really heavy. I put the same force on it. Is it going to accelerate as much? No. It's going to be actually a third as much, right? 3 times the mass is going to be a third of the acceleration for the same force, right? That's an inverse relationship. The more mass, the less it accelerates, okay? Now, oftentimes I think most textbooks you open, they tend to write it this way, F equals ma, right? But these are really the same thing, right? I like the fraction form. I think it explains cause effect a little bit better, but a lot of times you see it this way, F equals ma, okay? Net force equals mass times acceleration, okay? Now, if you were a more wordy kind of person, maybe you want to see it spelled out. So you might read this. The acceleration of an object. And what causes accelerations? Well, it's directly proportional to the net force acting on it. It's like that's it. And also inversely proportional to its mass, right? More mass, less acceleration, right? By the way, if you ever have two variables multiplied together on the same side, they have an inverse relationship with each other. And that's an example of that right there. It's cutting out. Is that working? Try this one. Oh, all right. I think it sounds a little better. Plugged in here. All right. And then finally, Newton's third law of motion. Oh, you guys ever heard for every reaction, there's an equal and opposite reaction? Right. Well, I'm going to reword that just a little bit because that's, this is where that comes from. For every active force on object A by object B, there is a reactive force equal in magnitude and opposite direction on object B by object A. So this weight's sitting here and I push on it with some force. Suppose I'm pushing with like 7.8 newtons. It's also pushing back on me with exactly 7.8 newtons, right? Those force pairs, or that force pair, I should say, has forces that are always equal magnitude, opposite direction, right? So that's a rule of nature. There's no such thing as pushing or pulling on something without getting an exactly equal and opposite force back the other way. Okay, right. You guys good with Newton's laws of motion? Okay, there we go. All right, you guys ready for some free body diagrams? All right, so flip my screen over, flip over here. Say present screen 2. All right. Okay, so I did introduce this idea to you guys, I think about a week ago. Right, so there you go. There's the definition of a free body diagram. Right, it's a diagram showing all the forces acting on an object. Okay. And what you want to do is always draw force vectors to represent the relative magnitude and direction of the forces, right? So there's an example here off to the side, right? Suppose you just have a weight just like sitting at rest, right? It has a weight pulling down. That's what mg is. I told you guys that last week too, right? Mass times gravity field could represent the weight of an object. You could also represent that F sub g, right? Force due to gravity, right? And what else am I showing here? I'm also showing what's called a normal force, right? Now it's called normal. Do you guys remember from math, from a math class? Guys, if two lines are normal, that means they're what to each other?
Parallel. Perpendicular.
Perpendicular, right? So a normal force, like a support force from a surface, is always perpendicular to that surface. Let me flip my screen back over and show you guys this. All right. So this weight sitting here, right? It definitely has a weight pulling down. That's a force, right? But see, if that was the only force, it would be in free fall. It'd be like, right, if I go to the edge of a cliff and just drop it, the only force acting on it would be its own weight acting down. Right? But if it's sitting here at rest on a table, well, it's in equilibrium. There's zero net force, so the forces have to be balanced. What's balancing it? Okay? It's got a weight acting down. And there's also a support force from the surface acting upwards. In fact, that support force is always perpendicular to the surface, and that's why it's called the normal force. See, if I did something like an incline situation, like if I had like an incline like this, that support force would still be perpendicular to the surface of that incline, right? In fact, it'd be less and less and less the steeper the skips, right? Which might eventually do with the guys, but right. All right. So let's flip back over to this presentation. So we got that, and see how those two forces are balancing out. Okay. Great. Right. Now, I've seen different textbooks and different conventions for drawing free body diagrams, but I do like AP's convention. So I've been converting over to that last few years, which is to draw a dot representing the center of mass of the object and just draw all force vectors extending from that. So I'll always just follow that convention from here on out. If there's some old material from like 5 years ago, then I might not follow that, but that's what I got. Right. Do you guys remember what forces are measured in? What unit? Newtons. We're doing newtons, right? And then American units are like pounds, but we're going to be using newtons, right? And I've got a whole presentation of these. I'm going to have you guys write these down as we're going along side by side. Okay? And you're only ever going to see force vectors, right? I don't care about velocity vectors. Well, except sometimes you want to know the direction of motion just to know, for example, that friction points the opposite direction of that. But then I really just care about that friction as a force vector. Okay? I don't really care about acceleration vectors, momentum vectors, displacement vectors. Right? All you care about for drawing your free body diagram are force vectors. That's it. Just forces. Okay? All right, guys ready to go on? All right, first one, block at rest on a table. Okay? That's kind of what we were just looking at, wasn't it? I was sort of guiding you guys through that. Block at rest on a table. Right. So try to give you guys a head start here. Can you guys draw that free body diagram before I do? Because if you can draw it first, that's a good indication. You know what's going on. I'm thinking of two forces acting on that block. Its weight. Did everybody just draw its weight? Acting down? Okay. Now, if I stopped there and just walked away, that block would be in free fall, wouldn't it? Kind of like I tossed it off the edge of the cliff. Which would not be at rest. At rest is a state of equilibrium. So I need something else. How about a normal force? Boom, boom, done. That could be a block at rest on a table, couldn't it? It's just sitting there.
You write this down?
Yeah, that's a good thing to write down. Right, block at rest on. I have also put this this PowerPoint on Google Classroom. So it is on Google Classroom for you guys too. But yeah, if you guys do like handwrite out the notes on a piece of paper, then help make some neural connections in your mind and stuff a little bit better. All right. How about this? What if there's a block at rest on a table? Okay, so yes, same situation as before, but somebody's pushing on it horizontally. Somebody's giving a little horizontal push, but it's only a small push. It's not even with enough force to overcome the static friction between the block and the table surface. Right. I bet this is pretty similar to what we were just looking at. I mean, I bet there's still a weight. Do you guys think there's still a weight pulling down? Do you guys think there's still a normal force holding it up?
Yeah.
Yeah. and there, it looks like there's some kind of pushing force, like an applied force, and also some kind of friction force in such a way that the block is still at rest, right? At rest, being one example of equilibrium, right? There's zero acceleration, so there's zero net force, right? Right. I'm thinking of four forces. Did you guys draw this weight, this normal force, this applied force, and this friction force? Right? Look at that. All the forces are still balanced out. They're still balanced out, aren't they? Right. Now, while you guys are digesting that and copying that into your notes, I'll tell you guys a little bit more detail about friction. So you guys see that friction force, that sideways friction force, F sub FR, compared to this normal force, the one point straight up, F sub N, normal force, right? See how the friction force is drawn shorter than the normal force, right? That'll almost always be true. There are a couple of weird exceptions to that, but that'll almost always be true. And the ratio of those two forces, especially if you're at like the breaking point of uh, where the block is about to break friction and slide across the paper, the ratio of those forces is important. In this case, that example I just told you guys, that would be called the coefficient of static friction, right? Suppose you're applying a force where it's just barely about to break friction. Like if you put any like micronewton of force extra, it would break the friction and start sliding across the paper, right? And the friction force has been building up to match that pushing force automatically, right? And it's just at the tipping point. If you do that friction force divided by that normal force, that would represent the coefficient of static friction. And just kind of eyeballing it, I might say it's about 0.4. It looks like the friction force is about, what, 40% of the normal force? Although I have a kind of a skewed perspective. I'm kind of off to the side. So I think that may be right. Maybe it's like, something like that. Okay, you guys good? All right, next slide. What if there's a block on a table being pushed horizontally so that the block moves with constant velocity across the surface? Now it is moving, sliding across the surface. Okay. So trying to give you guys a head start here. See if you guys can draw those forces before I reveal what the forces are. Again, just like always in this class. I mean, if you guys are staying a step ahead of me and you're getting the answers before I show you, that's a good indication. You know what's going on. Right. Did you guys draw a weight? Got to have that. If you don't have that, it's just kind of floating around, right? Did you guys draw a normal force? Right? So it's not like free fall plummeting towards the earth, right? It's some kind of support force called the normal force. Looks like we definitely have a horizontal table. Right? It is being pushed. So did you guys draw an applied force? Okay. Now, suppose I were to just stop there, right? So I draw that and then I walk away from the paper, right? What would be wrong with that free body diagram? There is a mismatch between this explanation in white letters up here and this free body diagram, right? Why do they not exactly match? It's one little detail. Okay, how about this? That free body diagram, as it's drawn right there, if I just stop right there, is there a net force on the block? Yes, there is. And it's a net force to the right, right? Now, vertically, the two vertical forces cancel out, but that pushing force would be to the right, right? And if there's a net force, is there acceleration? Yes. If there's acceleration, can there be constant velocity? Ooh, that's where it all breaks down. You guys see that? So I still need one more force to match this scenario of constant velocity, and that's what? Friction force. Friction force. That's the full answer right there. Right. You guys see how that friction force exactly balances with the pushing force? Right. Now, the fact that the block actually is sliding across the surface, right, which means it's no longer a static case. So this is like a kinetic case. So now the ratio of that friction force to that normal force is called the coefficient of kinetic friction. Okay. That'll probably eventually come back in this class, but I should for sure will, because I'm going to have you guys be doing the lab on pretty much that scenario right there. That scenario right there that you're looking at is going to become one of the upcoming labs, if not this week, then next week. Okay.
Is this going to be on the test rating?
Possibly. Right? You guys got that? Right, so while you guys are finished to copy that down, just to recap. Right, so block has 4 forces on it. It has a weight acting down, right, Earth gravity pulling it down, mg. It's got a normal force exactly balancing that out, support force from the surface holding it up. Those two cancel out for sure. Okay. Then there's an applied force, looks like pushing it to the right, and also a friction force. The friction force always opposes the direction of the motion. That green velocity vector is not actually part of the free body diagram, but it does give you context about the direction of that friction force, right? Which is always opposite of the motion, right? And in this case, I know the applied force and the friction force have to be balancing out each other because it says constant velocity. Constant velocity means 0 acceleration, means 0 net force. Okay? You guys got that? Right, next one. A block on a table pushed horizontally so that there is a net force. There is a net force. Right? I bet there's actually more than one correct answer to this, but well, let's take a look at one of the right answers. Do you guys think that there's a weight acting down and a normal force acting up? Just like the last couple slides, right? Those are balanced out. Okay, so it looks like there's no net force vertically. Right? It is moving across the table. Right? Maybe it's like, here, let's see what else we got. What if there's an applied force that's greater than the friction? Okay. Do you guys see this block like speeding up, moving to the right, speeding up to the right? Here's how I know it's specifically speeding up to the right. Right? Because the fact that friction always opposes the direction of motion means it must be moving to the right. Right? And the fact that there's a net force to the right and combined with velocity to the right means that it must be speeding up to the right. Okay. Guys get that? What about this? A rock in free fall with no air resistance. Rock and free fall. All right, so go to the edge of a cliff, drop a rock. All right, did you guys say this thing has a weight? Pull it straight down. Did you guys add any other forces? Or is that it? Is that the only force? That's it. That's the only one. Right? In fact, that's one definition of free fall, right? The only force acting on it is its own weight. That's the whole thing. Okay. What if you did this? What if you took this rock and you chucked it to the side so it goes into like a parabola type motion, like a projectile, right? And so the rock has already left your hand, and we're still ignoring air drag, but it's just moving in like a parabola type motion. Let's say kind of moving off to the side. Would that still be the free body diagram to describe that scenario? Yeah, it sure would. Right? Remember, your free body diagrams, all you care about are force vectors. What are the forces acting on the rock? Okay? You don't care anything about the velocity, okay? Except maybe to determine the direction of friction. But besides that, okay? How about this? Rock is in free fall. And now let's consider air drag. We almost always ignore that, but now let's actually consider that. So as the rock is falling, it's starting to build up some air drag against it. But let's say before it's reached a state of what's called terminal velocity. So do you guys think that as the rock is falling faster, 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 now that we're actually considering air drag, do you think the faster it's falling, the more the air drag is building up against it? Yeah, that is true, right? So we're going to be looking at a case where it's like in the middle of that process. Okay. So maybe there's a weight acting down, and there's like a drag force acting up, but see how I have the drag force as less than the weight, right? Like a smaller magnitude. Is that so? There's still a net force on this rock, right? It's just not its full weight, right? And the fact that there's a net force, there's still an acceleration, but it's not full. It's not the full free fall gravity of like 10 meters per second squared. Right? Okay, let me do a little calculation with you guys here. Right? Let's just eyeball the velocity vectors, these force vectors, and see if we can get an estimate of what the acceleration is of this rock. Okay? So suppose this rock has a mass of 1 kilogram. What is its weight equal to? Pretty close to. Do you guys remember how much 1 kilogram weighs at the surface of Earth? Well, the answer is kind of embedded in these variables. 1 kilogram of mass times a free fall gravity of about 10 meters per second squared. Wouldn't that give you like 10 newtons? Right? So 1 kilogram weighs about 10 newtons on Earth. Right? And it looks like this drag force is about half of that. So maybe I'll call this about like 5 newtons of drag force. Right? Guys, what is 10 newtons down and 5 newtons up? What's the net force? What's 10 minus 5?
5.
5. Do you guys think there's a net force on this rock of only 5 newtons? Now, if you kick back over to Newton's second law of motion, F equals ma, or rearrange that, A equals F over m. If you have 5 newtons acting on 1 kilogram, guys, what is 5 divided by 1? 5. And that would be meters per second squared. So it looks like this rocket is only accelerating at half the rate of gravity, isn't it? Okay. How about next slide? The rocket is in free fall with air drag. And let's say, like the last slide, it was still accelerating, right? Because there was still a net force. It wasn't accelerating as much, but it was still accelerating. So it's still falling faster, faster, faster. Now, let's say it's falling so fast that the air drag is picked up so much that it's exactly balancing its weight. Well, I'm sort of giving away the answer because that's what terminal velocity is, right? Boom. There's the answer right there. Is that right? Now, that rock right there, is that rock in equilibrium? Yes, it is, because all the forces are balanced. There is zero net force. Zero net force. That means zero acceleration, right? Newton's second law of motion, F equals ma. If there's no net force, there's no acceleration. Okay. Does zero acceleration mean zero velocity? No, those are completely different concepts. Right? So the rocket's still falling. It's just not picking up any more speed. You guys get that? It's just not speeding up anymore. Okay. Right. I want to do a graph with you guys. Let me flip the screen over. Flip over here. Flip back and forth one more time. So this class period. Right. So let's do a couple of graphs. Do side by side graphs. Let's do free fall with no air drag, which is what we almost always do in this class. Okay? And then we'll do a free fall situation, but I'm going to throw in, we'll say with air drag. Okay. Okay. And let's do a couple of graphs. We're going to do velocity versus time graphs. So velocity in meters per second versus time in seconds. Okay. Velocity, meters per second, time in seconds. Start with this graph on the left. Let's call a time 0. There would be 0 velocity, just to give you guys a point. So you go to the edge of the cliff and you drop a rock, or maybe I drop this lab weight. Edge of a cliff, right? And then just let go. So it starts falling, just all the way down. Okay, right. This graph on the left, everybody in this class should be able to do because we've done this a few times over the last few weeks. Okay. There's no air drag. What does this graph look like? Did you guys draw that in your notes before I show you? Okay. Okay, you guys should be able to do that. Did you guys all just draw that right there? Is that it? Is that what it should look like? Okay. And what's the slope of this? About 10 meters per second squared, as long as you're on Earth, right? We're more generally, the free fall gravity of the planet, lowercase g, right? You guys remember that? Like v equals gt, as long as you start from rest. The speed picks up too. So as time ticks, tick, 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 tick. All right. Okay, so that's all past that. Now let's get to the situation that involves air drag. Okay. And you guys know that the longer it's been falling for, the faster it's been falling. And air drag picks up more and more and more. Okay. The faster it falls. It's actually the air drag turns out to be proportional to the square of the speed. So if it goes like 3 times as fast, you have 9 times the air drag. Okay. Okay. Let me give you guys a couple of points. We'll still start off edge of the cliff. You drop the object, starts falling. So at time 0, it has 0 velocity because you dropped it. Okay. We'll call down positive. Right. And then I'm going to throw a point on this axis. I'll call this V terminal. Like as in the terminal velocity. Okay. So this is falling faster, faster, faster. The air drag is picking up more and more and more and more and more, right? Until at some point, finally, it reaches a state of equilibrium. It just goes down at constant velocity all the way down. Right. What's that graph going to look like? Here's what I'm thinking. I'm thinking it's probably going to start off pretty similar to the no air drag situation, because if this thing's just releasing from your hand or it's not moving very fast, probably the air drag would be pretty small. So it's going to start out kind of the same. This will still be rated G, the whole deal, right? Okay. But remember, the longer it's been falling for, it's going to not pick up as much speed as fast until it eventually reaches those horizontal asymptote. Now, it'll match that number, right? But it'll just go down at that terminal velocity all the way to the ground. Okay, here's a constant velocity. Okay, okay. So the graph on the left is what we've been assuming with no air drag, which is probably accurate enough, because as long as the air drag is not very significant. But the graph on the right is more accurate for if you have an air drag situation, especially if it's significant, you can reach that terminal velocity. Okay. It's really going on.
Is this going to be on a test?
Maybe. That'd be good to know. Okay. Now you guys, conceptual physics, I put more conceptual type questions on your quizzes. So there's gonna be a handful of maybe graphs, maybe calculations, just like the last couple quizzes. Right? You guys saw a handful of graphs and calculations, but mostly what you guys saw on your quizzes were those conceptual questions. So, actually, I have the packet right here. Okay. I did give this to you guys about a week ago, and on the other side are all these conceptual questions. Actually, it's 3 pages of them. Okay. So we're going to do some Kahoots in class over the next few weeks, where we cover all those conceptual questions, and those will be the most of your quiz questions. Okay. But yeah, any of this other stuff might pop up on a quiz. All right, so you guys got that? All good? All right, let's go back over here. Ooh, a boat moving through the water at constant velocity. I think I want to do this one a little bit faster here. Did you guys have a weight, a buoyant force? Okay, so the weight's pulling down, the buoyant force is holding it up. Did you guys have an applied, maybe an applied force? Maybe this is the propellers pushing against the water. Do you guys have a drag force? Maybe the water pushing back against the boat, kind of like friction, right? Like a drag force, right? And notice how all those forces are balanced out, right? The 2 verticals are balanced out, and the 2 horizontals are also balanced out because up here I said constant velocity. Constant velocity means 0 acceleration. 0 acceleration means 0 net force. You guys got that? Ooh, can you guys draw 3 forces acting on an object so that the object is in equilibrium? There's probably 100 different answers to this one. Okay, but trying to give you guys a little head start here. All right. So here's one of many solutions. You have like a 3-way tug of war. In fact, if you take that one and you turn it upside down, you guys did that in your lab last week. You guys remember that? Took the spring scales. This was one of the configurations you guys did, right? That might be like 10 newtons, 10 newtons, and 10 newtons, each at 120 degrees from each other. Right? Hey, here's another one. What if you have like 10 newtons up and then 5 and 5 down? Maybe something kind of like that. Pretty close. Okay. There's some other answers too. So again, it's probably 100 different ways you can do that. Ooh, a parachuter before terminal velocity. So the parachuter's falling down, has some weight. So he's just opened his parachute. You're starting to build some drag force up. But see, that snapshot right there, that's the entire answer, by the way. that snapshot right there is the parachuter still gaining speed, still speeding up towards the ground. Yeah, because there's a net force. The net force is down. See how there's more force down than up? Right? If there's a net force divided by the mass of the parachuter, you get the acceleration. So he's still accelerating. Now he's not accelerating at the full rate of gravity, but he's still accelerating. Right? Compare that to the next slide, parachuter at terminal velocity. So he's still got the exact same weight, but now he's just falling faster. Therefore, drag force is built up. Now, once the drag force matches his weight, now he's in equilibrium and he's done accelerating. Still moving down, right? Still has velocity. This has no acceleration. Okay. Is that? Okay. We do a couple more things here today. Okay. One thing is I want to give you guys some extra details about that parachuter, just for fun. Okay. And we'll do one more free body diagram after that. So this parachuter has a couple of forces on him. Okay. It's got its own weight acting down. We'll call it mg for weight, and a drag force acting up, F drag. Okay. Now that drag force is equal to, I've seen different variations on this equation, so I'll give you guys one of these versions. Okay. Coefficient of drag times density of the air times the area of the parachute times the speed squared. Okay. So coefficient of drag has to do with like, well, how about this? Do you guys know how you can design cars different ways or planes different ways and they have different aerodynamics? Okay, it's kind of embedded in that number. Okay, I'm more interested in some of these other things. So we got the density of air. Could you guys imagine if this guy was being dragged through the water? It would be like 1,000 times the drag force. Yeah, because water has 1,000 times the density of the air. How about this cross-sectional area? Cross-sectional area of the parachute. Okay, like this area right here, A, right? You guys think if this guy had like twice the size of the parachute, have double the air drag, right? And this V refers to the speed that he's falling. Okay. Notice that's being squared. So if he's falling at 3 times as fast, he has 9 times the air drag. You guys see that? Is that too? Okay. So that you guys don't really have to memorize anything for this class, but it is good to be able to, whether you Googled this or found this in a textbook, or again, there's different variations on that formula. Be able to pick it apart and say, okay, I see how to read the music of this equation, how these proportionalities work. Okay, we'll do one more. Okay, here's the last one we're doing today. A rocket moving constant velocity, 10,000 meters per second in deep space. It's just going, constant velocity, 10,000 meters per second. So free body diagram. What kind of vectors are the only kind of vectors you're drawing on your free body diagram? Do you draw velocity vectors? Do you draw momentum vectors? Do you draw displacement vectors? What's the only kind of vector you care about? Force vectors, right? And, do you guys see a very important detail in that set? It says constant velocity. Guys, constant velocity means the acceleration is equal to what? 0. If the acceleration is 0, what's the net force? 0. You guys are looking at the answer right there. There are no forces on that rocket. Hold on a minute. If there are no forces, that rocket's in deep space, right? Just screaming through space. 0. If there's no forces on it, what's keeping it going? Starts with an I. Inertia. That's all you need. You guys remember near the beginning of class, I told you guys about the Voyager spacecraft? Been going since the 1970s. What's keeping it going? Inertia. All right, and that is a wrap on today.